Hey, welcome back. I've got some food for you. I guess you're getting hungry doing all that work. Got to have good food though, protein bars, bit of fruit here, tinned peaches or something like that. Healthy stuff. Uh-oh, well, I don't think you can chomp away for too long now. We've got to get back to work. And why have I put them there? Well, really, it's about claims like this on packets. And all these little packets will have, and these cans will have some claims about them, about the net weight or the mean weight or of protein or of sugar or of fat or just of the fruit itself over here. All these claims, how are we going to test them? How do you know whether they're right? How does the manufacturer know what to put on the tin? Because you know that the weights are likely to be randomly distributed due to errors in filling and so on. In fact, you know, something like a smooth curve, if we represented the whole population, not just a histogram, the many, many thousands of cans or bars that we make are going to produce a smooth curve there. Just about every possible weight in between is going to occur, and you get a smooth curve, continuous variable. Well, maybe we wouldn't necessarily have a normal distribution of those weights. What are we going to do? How could we use statistical theory now and the normal distribution to actually test whether the claim is right? Let's go and have a look. Okay, let's check it out. Okay, and I'm going to suggest doing the following. Here's our protein bars, and we say it's very, very likely due to random errors in filling there, random variation in the production of these bars, that the weight of protein, or maybe it's the net weight of the bar either, this is the weight, is going to be normally distributed, weight in grams, let's say. And there's going to be a whole range of weights. And what's the manufacturer going to quote? The mean weight is, well, you know, if the manufacturer said the mean weight was 27 grams of protein, you know that some bars will be above and some will be below, depending upon the sigma, or the standard deviation, or the spread of that distribution away from the mean. How much are we going to allow them? Do we expect every bar to be 27 grams? No. What are you allowed to claim? Lots of legal questions here. Let's just check out whether the mean weight of protein in the bar is 27 grams. I'm going to suggest to you to check that out. We'll take a random sample of items and measure the weight of protein or the weight of the bar, whatever we're trying to test. We're going to therefore then calculate the mean. So let's say we take a sample of size n. Okay, we're going to take n bars. Okay, and we're going to find the mean x bar n. That's a statistic, isn't it? That's a calculation based on our sample. And then we're going to compare x bar n to the mu claim. What they claim is if you took their whole population of bars, this would be the mean. This seems to be a worthwhile activity, because we do want to know whether people are producing what they say they are. Now, I want you to brainstorm, maybe with your classmates. Would it work? Would that work, getting a number of bars and finding their mean? And how close to the actual value would we get of getting close to the actual mean of the weights of all these bars? And I think there's a clue in this diagram here where we can see the weights of the bars are probably going to be normally distributed around a central mean with a standard deviation. Okay, think about it, maybe pause the presentation and have a discussion about that. Okay, let's go down and see if we can analyse it now. And just down here I've drawn, oh yeah, you knew that was coming, a normal distribution. All right, so we've got the weights along here in grams. What we're going to do is going to take a sample from this distribution? Oh, well, let's start sampling. What would we do? Let's make it a random sample. So every weight value is possible to be included in our x bar n. This is a question now, isn't it? Did you realise that the first factor that's going to affect our mean and how close it is to the actual mean, here it is, of the population, which we don't know, they made a claim, that's a mean, let's call that of x, where weight is being measured as a variable. How close are we to that will depend upon the sample size. Let's just stick with a normal distribution for the moment. Let's say the weights are the variable normally distributed, hang on, I left out the end, mate. Normally distributed around some mean and some variance or sigma squared. Okay. I don't think 5 would cut it, would it? 5 samples taken at random could all end up over here. Be quite a way out, x bar 5. What do you reckon? Increase n is better? Better, is it? Because if we increase n, we won't be likely to have a few small ones or a few large ones. This would what? Even out? Even out the variation, not a very statistical term, but something you might think of. If the n was higher, even out the variation, what? Avoid bias, I suppose, because even though we are random sampling, if we only take a few, by chance they could end up in a low or high category and bias our sample. All right, what do you think? Large n, as large as possible, maybe do it more than once? What do you reckon? Let's have a look at some little graphs I've drawn for you here. Well, here we are. Now, in your view, talk about this with classmates. Where is n the largest? Which one of these? I'll tell you, one end is larger than the other for the n value. Which end? This end here, is that the sort of distribution you'd get for large n? Or this end? And the one in the middle is obviously in the middle. What's the different characteristics of these? Well, you're supposed to be saying that if we got our x bar and plotted it and it was of a certain size, it would be centred around the mean of the original population, I reckon. If they'd still even out to the mean of the original population, but one would be more tightly bound around it, wouldn't it? Which one's that? Sigma is smaller here. And this is the sigma of x bar. How what spread these means would be if we kept taking them of a certain size, and let's say that size was large or small, would you expect a bigger or smaller deviation? Because down here the variation or the spread is larger. Okay, and this is a spread of the x bars of a certain size n. If you took bigger n, what would you expect? To zero in or to be more spread? Well, the answer is, of course, this is the large n up here. If you took a large number of samples, you're not going to get much variation. The high and lows are going to even out. If you took a smaller n and here n smaller and got x bar n, then that could end up with values more extreme down here and here. That could be possible. If you take a large n, you're going to get more evening out. Let's go back and just have a look and see if we can see that from this original, hang on, just down here from this original distribution. So I'm going to do this better now and say, well, if I took 5 at any one time, let's take 5, I could get 2, 3, and by chance I might be over on this side x bar 5, so I could end up with an x bar over here, or they could be over here, okay, or it could be exactly evenly spread, x bar 5. Okay, so I'm still going to get a fair bit of variation in my means. And if I did it many, many times, come back down here, I don't want to make it dizzy here though. So this is if I did it many, many times, let's say n times, each taking 5 samples and 5 x bar of 5. I'd still have a fairly large spread here. Okay. N times big N means I'm going to do a lot of times, so I'm going to have a lot of points to plot around here. These are each themselves the mean of 5 samples. Well, hang on, what about coming up here and having a look? What does it look like if we take a larger N? Let's take something like 50. I think Hayes and Harris talk about this and say N should be larger than 30. There's no actual statistical reason for that. So I'm going to say, let's take about 50. That's a fair whack there. And let's say, sure, it's a random sample. Now, each time we do it, we've got to take 50. We get one there, we get one there, we get one there. Chances are, you're going to pretty much get one from everywhere, won't you? If they're random samples. Each member of the population has an equal opportunity of being included. And so what's their mean going to look like? Pretty close in here, I reckon. Don't you think? Very close to the actual mean of that distribution, mu of x. So we would expect the bigger n, okay, n larger, we would expect our x bar n to tend to, mu of x with a smaller sigma, okay, because of the evening out, if we can say that. Evening out. Doesn't look right, does it? You're not going to have an evening out, are you? You can't afford to go out. You haven't got the time. You've got your homework anyway. Well, different evening, I think. Anyway, the scores are going to even themselves out around a centre here. And so that's what we're trying to investigate. So we'll need a fairly large sample size so that we get this sort of zeroing in. We're going to take n large, so the x bar n gets very, very close to the mean of the original population. This is very much trying to estimate what is the mean of the original population. Now, we'll do it n times. N times we will choose what? N, maybe 50 samples, and find the mean. Okay. We do it many, many times. We're going to have lots of points along here, all very close together, and we'll have that continuous distribution if you did it many, many times. All the histogram widths become smaller and smaller, and you end up with a smooth curve, if you like. So it looks like, to answer our question, we really should take a pretty large sample. Okay? How large? We don't know. It's still the same thing. Depends on how skewed the original distribution is and other factors as well about the variation in that particular variable. All right. It's getting interesting, isn't it? We're trying to work out a way of estimating this unknown value. And this worries some people in statistics. Okay, because you can't come up with a definite answer. Let's come down now and have a look at Hayes and Harris screen clippings here, and let's try to do a little bit more formally now. So we're saying this is important, even if it's a wacko distribution, non-normal. This distribution is not a normal distribution. Let's try and investigate what's going to happen. Let's take our first sample over here. We take n items. Let's say that's a large number. They haven't indicated what it is here. Let's say it's around 50. We take 50 items and get a mean and plot it down here somewhere. Then we take another sample. and plot it. And this one is down here at x2, and we're going to do it many, many times, so there's going to be a frequency of those if you like. Sample 3 tends to be a bit further out. Okay, by chance, a lot of the sample 3 items randomly chosen were on the top end, giving a higher sample mean, and one down here lower. And so we've got a bit of error here. We can see that the mean of the mean, so that's what this is, if we kept doing it for the whole population of x bar 50s, in other words, take an infinite number of samples of size 50 and plot their means, so we're going to do this n times, where n's going to tend to infinity. We go and do it, we're going to be very tired here, mate. We go and get 50 samples measured, find their mean, and get 1 point. Then we do it many, many times and we plot the overall results. Now all of those x bar 50s are going to end up giving us this sort of curve, a normal curve. We're not going to talk about why that's the case in this course, but to give you some idea. The x bar 50 is taken at random from the population, so it's going to suffer random variation. Around what centre value? Should be around the centre of the original distribution, shouldn't it? The mean, not the centre here. And this is probably the mean would be the best measure in a non-normal distribution of the centre. But the mean here is going to be that value, and as we take these bundles of 50, reasonable size n, and plot the means, they're going to zero in. You're not going to get scores so much out this end, because to get a mean there, they would have all had to come basically from one end or the other. You're going to zero in here on the mean. Do you get it? So what we usually write is that the mean of the distribution of means, in other words, you're plotting a curve which shows the result of all your means of 50. So you've done a lot of work. This will be approximately equal to the mean of the original population. And the sigma of the x bars is going to be less than the sigma of the original population. It's going to zero in because you're plotting means, and they're going to even out the variation from the top to the bottom. You're not just plotting those extreme scores now. You're adding up about 50 of them, let's say, and finding a mean. Do you get it? Let's come down and see what we can say about that. Here it is here. And we'll just include the central limit theorem here, I think. Okay, so what's happening? If n is smaller, that's the sample size that we're taking the mean of. We're taking x bar n and plotting that value, not x's anymore. N larger, we reckon the standard deviation, the width there, one standard deviation away from the mean, remember, is that point of inflection. We're talking about n larger, that's a larger sample size, it will narrow, and n, this will be the n, the largest one of the three here, is the smallest standard deviation, okay, of that distribution of means. Now just keep in mind, look at the shapes of the distributions here. This is something that was wrong with my diagram, wasn't it? Here, if there's a larger standard deviation, it won't be as tall because the area has to be 1 underneath. If there's a smaller standard deviation, it's got to be taller. Mine were all done to a different scale up there. So you might get some idea there that the shaded area has to equal 1, the total sum of all the probabilities there. Okay. So what's the central limit theorem say? This is a powerful tool used by consumer affairs in testing products. So it's very, very important. So if x is a random variable which is not necessarily normally distributed, so you could have quite a wacko distribution, but if that has a mean of mu and a standard deviation of sigma, if you take big enough samples and plot the mean of those, Okay, so you're taking something like maybe 50 and plotting the means, then those means will form a normal distribution, even if they didn't come from a normal distribution originally. And the mean of that normal distribution of means will be equal to the mean of the original distribution. And the spread will equal sigma on root n. So can you see, if we enlarged n, we get a smaller sigma. And that's coming back up here. That's what we're saying in this range of graphs there. We're zeroing in. The variation in the x value that we observed originally is going to be evened out by taking the means. Okay, very important result. Let's go down and see another little definition. Here we go here. The standard deviation, sigma x bar, which is the original sigma of x divided by root n of the sample means, is a measure of the variability. Yeah, that's how much they vary, or a spread, isn't it? Standard deviation is the spread away from the mean. In fact, it's the square root of the mean of the squares of the deviation of individual scores away from the mean, if you want to get technical. Anyway, so it's called the sampling error or standard error. Why has the word error crept in instead of standard deviation or spread or something like that? Do you get it? It's what we were trying to do back in our original problem. We went out and measured 50 and we had an estimate of the population mean, but it would have had an error, wouldn't it? Because when we do those 50, let's say, they are still spread. They're not all going to come out to be this. And this is what a common layperson doesn't understand. They go out and take 10 of something and say, hey, my mean's 20. They said it's 25. That's wrong. Okay, well, it isn't wrong because there are sampling errors. By chance, it depends on which group you take as to what you will end up getting. To actually check it out, you would have to take the whole population. As soon as you do sampling, here it is up here, as soon as you do sampling, depending on where those samples come from, even if at random, equal opportunities for all members of the population, you don't necessarily end up right on the actual population mean. So mu x bar should be close to it, but there will be this error, this standard deviation here. That's called the sampling error, because this course is very much focused on the idea that if you go out to test the mean of something, you take a bundle, they won't be giving you a mean exactly equal to the population mean necessarily. There will be a normal distribution around a value which should be centred pretty close to the mean of the population. So, distribution of sample means. A very important idea in this course, and that's what the whole of our inferential statistics is centred around in this course. We're going to go on now and talk about errors and how we can estimate errors in this process of checking a population mean. So please keep that in mind. We're checking a population mean. So let's have a look at this first little exercise. And that's saying, if we have a random variable and it's normally distributed, it's got a mean and a standard deviation, let's have a look at what we'd expect if we took a sample of 20 and found their means. First of all, let's find the chance of an ordinary member of that population being between 35 and 45, whatever those things are that we're measuring. So what we're doing here is the same as before. Here we go, the mean is 40 and the standard deviation is 10. This is of x, mean of x, sigma of x. So between 35 and 45, that's one standard deviation either side. We know it should be looking something like that, 35 and 45. Oh no, that's not one standard deviation, is it? No. It's 5 and 5. It's half standard deviation either way. And the probability is 38%. Okay. Now let's have a look at what does this mean up here. It says if we took 20, take 20 at a time and find their mean, what's the chance of that lying between 35 and 45? What's your gut feeling? Gut feeling. What's your gut feeling? Let's have a look. We have a distribution which is skinnier, still centred around a mean of 40 x bar and a standard deviation of what? 20 on root 20. No, deviation was 10. The sample size was 20. Let's just change it. 10 on root 20. That's going to be smaller and narrower. Okay, so they won't be as spread. More of them will be bunched in the centre. So between 35 and 45, we would expect most of them. So what are we going to do? We'll go and work that out with NCD. The lower will be 35, the upper will be 45. The sigma, and you can put that in here and it'll calculate it in situ for you, and the mu will be 40. So in other words, you're working on a different distribution. Come over the other side over here. You won't be working on the distribution of raw scores, the original scores. Because when you take the mean, come back over here, got you jumping everywhere here, when you take the mean of 20, the standard deviation of those means is less. So it's going to come to a much higher percentage, for sufficiently large n, and we still don't know what that n is, but here we had the advantage the original distribution was normally distributed. So that's going to give us a normal distribution. That's not as hard to see as when it's a wacko distribution. Let's come down and have a look at another one. The time t it takes to serve a customer. So there's our variable at a railway station is normally distributed with a mean of 45, standard deviation of 20. You only have 10 minutes to buy your ticket or you'll miss your train. There's a line of 11 people. This is interesting. What's the probability you will catch the train? Okay, how would you do that? Well, you're working on averages, aren't you? Averages in everyday language implies what's going to be the mean waiting time. Okay, well, first of all, there are 12 persons, including yourself. You've got to be, have your ticket bought within 10 minutes, less than 10 minutes. So, the mean serving time has to be less than what? Well, you've got 10 minutes, 60 seconds a minute, divide by the 12 people, including yourself, is approximately 50 seconds. So the x bar of the 12 people, including yourself, is approximately 50 seconds. Okay, so we're interested in what's the variation in t bar 12. Well, I should really change that. They've called it t now, not x, haven't they? So I should maybe put t12 there. So how is t12 distributed? Well, the original distribution was normal. This will be normal. And t bar 12, the mean of that will be approximately equal to the original mean, 45 seconds. But the sigma of t bar 12 will be approximately equal to, now what will it be? It was original 20 seconds, but because it's a distribution of sample means, divide by root 12. Okay, it's a narrower distribution. Okay, so if this is the t bar 12 distribution, then we need to put in these values. What's the probability of being, less than 50 seconds? So NCD. Lower would be neg 99. Upper would be no more than 50 seconds. Sigma, this is the one that's got to be changed. 20 on root 12, and the mu is 45. So the important thing here is that the t bar 12 distribution is narrower. So if you're talking about means, sample means of a sample of a certain size, then you must adjust the distribution on which you're working. Okay, so we will then come out with a probability, and they've done it over here. You've got an 80% chance of getting that train on time. All right, I'll give you a go now. Let's come down and have a go at these. Now, they're talking about a random variable and then talking about the probability of a mean of 10 or something of them. So adjust the distribution. Adjust the distribution going from there to there. Adjust. Okay, this is the probability of getting one of the original scores, one of the original measurements between 75 and 85, and this is the probability of getting a mean of 10 of them between those values. Remember, the distribution is narrower, if you like, evened out, and sigma is now, sigma of the x bars is a smaller sigma. Narrow. So work out your probabilities on this different distribution. Okay. Same thing here, and compare the probabilities of the original distribution with the distribution of sample means. Okay, come down now and let's look at the answer. Question 5 and 6, I think 7 fits on. Yep, 5, 6 and 7. So look at it carefully and just check that you have adjusted the distribution. Adjust the distribution, because it is narrower now. The distribution of means, because they even out around that central value, will have a smaller standard deviation. All right, are you getting it? Let's keep going and see what other interesting problems we can solve. Here's one here. 2 histograms of sample, each of size 400, are shown below. One is from a uniform distribution with mean 10 and standard deviation 5.77. The other is from a distribution of the sample means selected from the distribution. Note that the scales are not the same in the 2 diagrams. 50, 30 here. The scales at the bottom are different as well. This goes up to 20, this goes up to 13. So there's a few properties that are different here. Which of the 2 histograms is from X bar 36? That is, it represents a plotting of the mean of 36 items many, many times. Give reasons for your answer. From the diagram, estimate the probability of getting a mean which would be less than 9. Find the approximate mean and standard deviation of X bar 36, and use histogram to estimate the probability that X bar 36 is 1 standard deviation from the mean. All right, let's go and have a look. This is a type example, so we'll go through Hayes and Harris screen clippings here. The data in histogram A is less spread out than the data in histogram B and appears to be clustered around 10. Histogram A is histogram for the distribution of X bar 36. You might also say by the central limit theorem, if n is sufficiently large, then it'll be approximately normally distributed. Okay, and histogram A is approximately normally distributed, which under the central limit theorem is expected, isn't it, when we plot the means? Let's just go up and look at that distribution again. There it is, histogram A. It is less spread, less variation, but also it is normally distributed. Okay, approximately normally distributed. So make those 2 observations from the central limit theorem. To find the probability X bar is less than 9, you could count up all the numbers in all the bins before this one here and use factor of 400. So they've counted up all the groups up to that one and then divided by 400. So this is a approximation from the statistics that we've gathered from the sample there. Okay, now the central limit theorem should be quoted here by CLT implies X bar 36 will equal mean of the x's will equal 10. Well, actually what we should be putting there is mu X bar 36. In other words, the mean of the distribution of all the possible samples of size 36 will zero on the mean of the original value there, and the sigma of x bar 36 will be approximately the sigma of the original x's divided by root 36 under the central limit theorem, as long as n is sufficiently large. So this will be approximately 0.962. So you're often asked to show that in exams. So you must quote, by the central limit theorem, this statement must be made before putting it equal. Because often it's to show that the means would be distributed with a mean of 10 and a standard deviation of this. So you have to say, by the central limit theorem, show that you are stating that the means are the same and the standard deviation would be original standard deviation divided by root n under the central limit theorem. This is usually 2 marks, but there are actually 3 points here. This is point 1, point 2, and show the calculation of the difference there, point 3 out of 2 marks. So just watch that. Okay, and then what's the probability of being one standard deviation either side of the mean here? That's 10 minus the standard deviation, 10 plus the standard deviation, and so you could do it crudely like that, about 72%. This is from a sample, isn't it? Adding up all the numbers in those columns, or the frequency of those groups there, and dividing by the total. And if you did it on the calculator, you would get, of course, approximately 68%. But here it's 72, because we're doing a rather rough estimate of that. And we're limited sample size. It's a big sample size, but it needs to be a lot bigger if we're going to get that estimate of the continuous variable. Okay, come down now and have a go yourself. Okay, so here's a few problems, again from Hayes, and Harris. It's question 1 and 2, or 1. I'll bring up the rest of 2. We'll show you the solutions in a minute. So come up the rest of 2 there. And coming on, there are the answers. Okay, so have a go, see what you think. Need to build up these skills. You can see some useful ideas here and being able to test claims. And that's where this gets exciting, this work, in the next couple of presentations, where we really get into trying to find a really good estimate with a probability of error for our population mean through looking at our distribution of sample means. Okay, so here we have a couple of little examples here. Age of men in Australia is distributed with a mean of 43, standard deviation of 8. Sample of 67 men is taken. What is it probably? Oh, sample mean, there's a clue. Adjust your distribution, adjust the distribution. We're talking about the expected variation in a bundle, or in the mean of a bundle of 67 of them. So, what is the probability the sample mean is less than 42? Well, first of all, we would say n is probably sufficiently large. We're going to assume that. So therefore, we say the mean is approximately normal, we're distributed with a mean of 43, standard deviation of this. So there we are, mean of 43, a sigma equals 8 over root 67. So we shaded in what's the probability of somebody being less than 42, getting a mean of 67 men less than 42 years old, and so that's the NCD on the Casio, lower, neggy 99, upper is equal to 42, sigma, adjusted distribution, 87, 8 over root 67, mean of 43. Remember, it's narrowing down. The distribution of mean is going to be a much narrower population than that of the actual ages, individual ages. That would look much more like this. Oops, it's normal distribution here. Oh no, we don't know it's a normal distribution, the age of men here. So it could be like that. Much more spread, still centred sort of around the same value. I don't know, that looks like that might be a bit top heavy there, so Could be like that, I don't know. But the mean's going to be the same. It's going to be much more spread. We don't even know up the top here that it's normally distributed. And it doesn't matter, because under the central limit theorem we know if we do that sampling, we do get that random variation and the means will be normally distributed. Okay, what about greater than 45? Well, it's the same thing. It's this upper tail. Just remembering the mean is 43, the mean of the x bars, the sigma of the x bars is the one that changes, 8 over root 67. Okay, don't forget, adjust the distribution. Okay, between 40 and 45, same thing. It's all worked out on a distribution of what we expect the sample means if we did it n times, big N lots of x bar 67. So we take 67 people, find the mean, and then do it many, many times, we would get this sort of distribution. This is a distribution of all the possible means of 67 people. Okay, let's let you loose on some problems now and see what you think. Okay, 3 through 7. This is a sort of problem that's very important in this course, this idea of looking at the variation in sample means, eventually with the idea of collecting a mean to test a proposition. Okay, pause it. I'm going to show you the answers now. Okay, so here's a few, 3 through 6. Have a look to see if you can get those probability answers there. Okay, if not, make sure you adjusted for x bar distribution, x bar n. Okay, all right, let's do the last little one here, 7. All right, let's go on. Only a little bit, an interesting little problem to finish off with here, interesting little type. A population known to have a standard deviation of 8, but has an unknown mean, mu. In order to estimate mu, the mean of a random sample of 60 is found. Random sample, mean, x bar 60. Now, 60 sounds reasonable size. They use 30, that's questionable as a measure. But anyway, 60 is a fairly large sample. Now, if we assume that x bar is normally distributed, that's under the central limit theorem. Supposing that n is sufficiently large. Should always mention that. So assuming 60 is sufficiently large under the central limit theorem, this will be true. And we want the probability that the estimate is out by less than 2. Okay, unknown mean. Now we said before we usually use z-scores for unknown mean, and that's true, because we want an unknown mean, so this is x bar minus mu, alright, so we've got a mean, minus the original has to be out by 2. So x bar minus mu, our mean away from the population mean, will have to be out by less than 2. Neg 2 is less than x bar minus mu. So that's a clue. Our difference makes us think, oh, we don't have a mu, so we're going to divide by sigma on root n, because this is a z-score now for distribution of means, isn't it? So we don't know this here, but we do know the sigma of x bar is sigma x on root n. So we're going to do a z-score on this distribution with a mean of x bar unknown. So it's the same z-score idea. We're going to divide through by 8 on root 60, and therefore we're going to look at what's the probability of getting a z-score, because that's a z-score, between this value and this one. So whenever you have an unknown mean, in some way or another, you do need to revert to z-scores. You just have to adjust your distribution. The distribution of sample means has a different sigma. Sigma x bar is sigma x on root n. Don't forget to adjust that. So when we now move that back to find a z-score, it's this one, x bar minus mu on sigma x on root n. So this is an interesting little variation. So come and see if you can do a couple, and then we'll finish there. There they are, 8 and 9. And just see what we're trying to do? It's all centred around this questioning. People say, on the average you get this, on the average you get that. You are now empowered to actually find out whether there's error in that, estimating the amount of error. And budding young mathematicians get frustrated. They want to know the actual error. But remember, we have random variation here. We've got a continuous variable. We cannot actually measure the truth without measuring the whole population, and so it's going to be a bit out there, an error, a probability of it's going to be out by a certain amount. A sampling error, if you like. By chance, are we going to get values centred right on the same mean? No. Random variation, chance, sampling or chance variation here in our values. All right, let's have a look, pause this, and then let's have a look at the solutions. All right, here we go. Here are the solutions. Check your work, go back. Don't forget, when you're talking about means, you've got to adjust the distribution for that narrower variation. Remember, evening out. The scores are evening out. And I reckon, just between you and I, buddy, after doing all this work, you definitely deserve an evening out. Anyway, that's the last joke for this presentation. We've got 2 more interesting tests to do in the next presentation to really ramp it up into a level of sophistication that you will be proud of. So keep working hard, but for now, it's cheers from me.